Let us see this problem. We are given a set as an array and a sum. We need to find out count of subsets of this array whose sum is equal to given sum. Let's first define what is a subset. If we have an array of size 3, then it's going to have 2 raised to the power 3, which means 8 subsets. Subsets are empty, 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. If your array size or set size is 4, then it's going to have 2 raised to the power 4 subsets. For n-sized array, the number of subsets are 2 raised to the power n. We consider empty and whole array also as subsets. Now let's take a look at our problem examples. We have this array 10, 5, 2, 3, 6, and we have the sum as 8. So if we generate all the subsets of this array, we can notice that there are 2 subsets whose sum is 8. One subset is 5 and 3, and the other subset is 2 and 6. Let's see this example. We are given sum as 4, and there is one subset whose sum is 4, 1 and 3. Let's see this example. We are given sum as 37. There is no subset whose sum is 37. The subsets are 10, 20, 15, 10, 20, 10, 15, 20, 15. All these subsets have sum different from 37. None of them have sum 37. So output is 0. There are 0 subsets with sum 37. Let us see this corner case example. We have a set with 3 elements and sum is 0. Output is 1. Why 1? Because empty set is also a subset of every set. So if somebody passes sum is equal to 0, you can always print the output as 1, because empty set has sum 0 and empty set is a subset of every set. Now please pause this video and try to write down a recursive solution that finds count of subsets with given sum. Let us now talk about the idea for the recursive solution. Let us consider this example set and this sum. For these values, we are going to follow a recursive approach that considers 2 cases for every element. For every element, the 2 cases are, it is either included in the current set or not included in the current set. This is how we generate all subsets of a set. We can traverse the elements either from the left side or from the right side. In this recursion tree, I have traversed from the right side. For ease of implementation, I am going to use the size of array as index. So I am going to always consider array n minus 1 and going to decide whether to include it or not include it. So we begin from the last element, and initially we begin from an empty set. Now we consider for the last element 2 cases: not to include it or exclude it, and include it. So our current set is empty and 15 only. After we've decided for the last element, we move to the next element, 20. And we again make 2 choices for this in every case. We exclude 20, we include 20. We exclude 20, we include 20. When you exclude, you just copy the above set here. And when you include, you copy and add 20 to it. Now we come to 10, and we have 2 cases again for everything. Here, exclude 10, include 10, exclude 10, include 10, exclude 10, include 10, exclude 10, include 10. And now if you see, here we have all the subsets of a given set. We have empty, 10, 20, 20, 10, 15, 15, 10, 15, 20, 15, 20, 10. So there are 8 subsets of an array of size 3, and we have all the 8 subsets here. If array size was 4, then we would have 5 levels and 16 leaves, and those 16 leaves would represent 16 subsets, or 2 raised to the power 4 subsets of the given set. Now we just need to write a recursive solution that takes the input array and size of the array as an argument. For last element of this array, it makes 2 recursive calls, one recursive call excluding the last element, one recursive call including the last element, and reduces the array size by 1 in the recursive calls. So then it will make recursive calls for n equal to 1, and finally it will make recursive calls for n equal to 0. When you make a recursive call for n equal to 0, it means you have considered all the elements, you have considered from last to first every element, and you've generated all the subsets. Now for current subset, you just need to check whether sum of the subset is equal to given sum or not. If sum of the subset is equal to the given sum, then return 1, otherwise return 0. And in the parent calls, you just need to sum the values returned by these two calls. So here you will return the sum of this call and this call. Here you will return the sum of this call and this call. So this is the idea for recursive solution. Now please pause this video and try to write down a recursive code. Let us now see the implementation of the recursive solution. This is slightly trickier implementation. A simple implementation could have been maintain current subset as a vector in C++ or an array list in Java. When you are at the current item, you make two choices. You don't include it and you include it. When you don't include it, you do not add it to the current subset. And when you include it, you add it to the current subset. So in your vector or array list, you maintain these items. Here, instead of maintaining a separate vector or array list, what trick we have done here is we have used the sum variable. So initially we are passing sum as 25. Now when we are at last element and we are making two choices, what we do is when we don't include it, we do not change the sum variable in the recursive calls. So this is the case where we don't include it. And when we include it, we subtract this item from the sum. So we subtract 15 from 25. We have sum as 10 in this recursive call. Now again, when you don't include the current element here is 20, right? When you don't include it, you pass the sum as it is 25. When you include it, you subtract this element 20 from 25 and you get the sum as 5. Here again, your next element, this level element is 20. When you don't include it, you keep the sum as it is. And when you include it, you subtract 20 from it, your sum becomes minus 10. Again, at the next level, we consider the next element 10 and we consider the two choices for every subset. When we do not include it, we simply take the sum as 25. When we include it, we subtract 10 from 25, we have the sum as 15. Here again, when we don't include it, we copy the sum as 5. When we include it, we subtract 10 from sum, we get minus 5. Here again, copy and subtract 10, copy and subtract 10. Now when you reach the last level, when n becomes 0, it means you have processed every element and whatever you have right now is your final subset. Nothing more to be processed. And at this level, if you have sum equal to 0, then this subset corresponds to a subset whose sum is equal to the given sum, which was originally given to us. And if you notice all these subsets, this particular subset recursive call has sum equal to 0. So for this case, we return 1. For all the other cases, we return 0 because they don't have sum equal to 0. They have something else as sum. And that's what we have written here. We are making two recursive calls. And in this recursive call, we are not including it, which means we are simply keeping the sum as it is, but we are removing this element from the next recursive calls. In this case, we are including it into the sum. That's why we are subtracting it and we are making a recursive call for n-1 elements. We keep doing these recursive calls. So this is how it will process. At the end, what will happen? You would have processed every element, your n would become 0. When n becomes 0, you simply check if sum is 0, then return 1, otherwise return 0. So all these ones, if there were multiple subsets, they would be accumulated in the recursive calls and you will get count of all these subsets. Please note that in this recursive solution, we are not maintaining these subsets. We are maintaining this sum variable, and using sum variable, we are able to decide whether we found a subset with given sum or not. If sum becomes 0 by subtracting the elements of the current subset, then we say we have found a subset whose sum is equal to the given sum. That's the idea we are following. Also, this implementation is a very basic implementation and it can be optimized in many ways. We can optimize it using backtracking. And we can also write a dynamic programming solution that is pseudo-polynomial. Before we talk about the optimized solutions, let us analyze the time complexity of the solution. If you take a look at this recursive solution, it's going to follow this recursion tree. And how much work it's going to do? For n element array, you are going to have 2 raised to the power n leaves. and then you are going to have 2 raised to the power n minus 1 internal nodes. So the amount of work it's going to do is 2 raised to the power n recursive calls for leaves plus 2 raised to the power n minus 1 recursive calls for internal nodes. For example, if n is 3, you will have 8 recursive calls here, and then you will have 7 recursive calls here. You will have total 15 recursive calls. And if I put it in asymptotic notations, I'll get theta of 2 raised to the power n. That is the amount of work we are doing in this recursive solution. In an upcoming video, we are going to talk about a dynamic programming solution for this. The time complexity of dynamic programming solution is going to be n into sum. You might want to try the dynamic programming solution yourself.